We are back, lecture 44 today. 44 out of what I think will be about somewhere in the low 60s before all is said and done for this course. We have a couple web-assigned questions, and we'll try to find out what the issue is with them, and then we'll go back to Appendix F, which deals with sigma notation. Might seem a little odd that we're addressing sigma notation when we're going into a section, actually the rest of this course certainly, is on anti-differentiation. There is a tie between sigma notation and anti-differentiation. So we'll get Appendix F for the sigma notation. Might be relatively new for some of you. Hopefully enough of it there in this book in the form of an appendix that we can use it. And then we'll tie that together with antiderivatives in the form of finding areas under curves, which is the first application of antiderivatives. So before the appendix, I've got a couple web-assigned questions. It's my understanding this is due tonight for the folks in here. So we are given that the second derivative of a function is x plus square root of x. We also know that the f of 1 is 1. Does this change from one person's homework to another, or is this the same?
It's the same.
F of 1 equals 1. Does that look familiar?
Yes.
F prime of 1 equals 2. So what is this stuff for? F of 1 equals 1.
To put your C and D
Okay,
in.
to find the C values. We're going to accumulate, if we're working our way back from the second derivative back to the original function, which is the goal, is to find f of x. We're going to have a constant the first time we anti-differentiate, and another constant the second time we anti-differentiate. So we've got to have two pieces of information that are going to help us. All right, so let's, if we have f double prime, let me rewrite that as x plus x to what power? To the 1/2 power. And if we want f prime, we can anti-differentiate. What's the antiderivative of x?
1/2 x squared.
Okay, x squared over 2, or 1/2 x squared. What's the antiderivative of x to the 1/2?
2/3.
X to the 3/2.
Okay, I've heard both those are both right. X to the
3/2
over 3/2. Some of you said 2/3 of that, which is the same thing. And then we'll have a constant, right? Some arbitrary constant. So it's not an answer. It's a whole bunch of answers. But let's figure out which answer it is by this fact right here, right? So when x is 1, the derivative is 2. So for the derivative, we'll put in 2. And everywhere we see an x, we'll put in 1. I'm going to move that division by 3/2 up here and call it multiplication by 2/3. So we plug all that stuff in. We can find, hopefully, C1. 2 equals 1/2 plus 1 to the 3/2 would be the square root of 1, which is 1 cubed, which is still 1. So it looks like 2 minus 1/2 minus 2/3 is C1, which is what?
We got 5, 6. No. Yeah, -5, 6.
Negative 5, 6?
Yes.
2 minus 1/2 is 3/2.
Yes.
And if we're going to subtract 2/3, then we multiply here by 3 and 3, and here 2 and 2. So 9 over 6 minus 4 over 6, 5 over 6,
Yeah.
positive.
Oh, it's positive.
So that goes back up into here. So instead of having a family of curves represented by f prime of x, we now have one answer. So f prime is 1/2 x squared plus 2/3 x to the 3/2 plus this C1 value, which was 5 over 6. Does that work? Was that a sign error? Did you catch it? No, we're
No,
still kind
hold
of
on, let me
okay.
plug it in.
So now we have f prime. We want to work our way back to f of x, so we anti-differentiate again. Bring the 1/2 along. What's the antiderivative of x squared?
3/2 x to
X
the
cubed
third.
over 3. Is that right? Bring this 2/3 along for the ride. What's the antiderivative of x to the 3/2? X to the 5/2 over 5/2. This is important why we found C1, because now we need to anti-differentiate C1, which is
5x over 6.
right, 5x over 6 or 5/6 x. And then we have the possibility of another constant. Does that work? Everybody all right with that? And then we have this additional piece of information right here. When we put 1 in for x, the f of 1 is in fact 1. So for the f of 1, we'll put 1. 1 cubed over 3. We're going to have a 2/3 and a what? Division by 5/2, which is multiplied by 2/5.
Yes.
1 to the 5/2 plus 5/6 times 1 plus C2. Getting a little crowded there. Let me move it to the next page. So we have 1 equals 1/2 times 1/3, which is 1 over 6. 2/3 times 2/5 times 1 to the 5/2, which is also 1. So what do we get out of that? 4/15.
Yes.
And 5/6 times 1 and plus this C2. So 1 minus 1/6 minus 4/15 minus 5/6 is C2.
Minus
4/15 x to the 5/2.
negative 4/15.
Got a consensus? Negative 4/15?
Yes.
So that should do it. And you said you got that, and it's not accepting it. It's probably just maybe a format
I'm going to
syntax error or something. Sometimes it's browser specific too. If you're working in Netscape and if you just switch to Safari and send in the same answer, it'll take it. I don't know the reason for that. But the important thing is that we've kind of analyzed that you are doing it right, the procedure. Any questions? Built-in checks. Do we have any built-in checks? You could take the derivative of f prime, right? Here's our f prime. Take the derivative and you should be back here, right? You can take the derivative of f, so our final answer. You can take the derivative here and you ought to be back to what we came up with for the first derivative. So you kind of have two built-in checks. Do we still need to do the other one? It's got a sign in it. All right, let's get it started, and you can take it from there. Again, f double prime is given. Is that a 5 sine of x? We also know that the f of 0 is 1, and the f prime of 0 is 2. I notice on both these examples, they give you the same x value in both cases. That is not necessarily going to be the case, but they're doing it on these two examples. Instructions are to find f of x. All right, let's start by finding f prime of x. What's the antiderivative of 3 e to the x? 3 comes along for the ride. Antiderivative of e to the x is itself. 5 is the coefficient, so it comes along. Antiderivative of sine. Good. Negative cosine. So what has sine for its derivative? That would not be cosine. That'd be the negative of the cosine. And then we have the possibility of a constant. And we use this piece of information. That's probably why they picked 0. I guess they could have picked 0 and then maybe pi over 2 or something else, but we're going to have to take the cosine of it. And we're also going to have to raise e to that power. So when we put in 0 for x, it should kick out 2 for the f prime. So 2 equals e to the 0 is 1 times 3 is 3. What's the cosine of 0?
1.
1, so minus 5 plus c1. So c1 is what?
4.
4? Is that right? So we would put that back into there. And the process would then iterate again, right? Take the antiderivative again, and when you plug in 0 for x, it should kick out y, a y value of 1, an f of 0 value of 1.
The previous one is wrong on the other side.
The previous one with the negative 4/15 is wrong because you submitted it and it didn't like it, or we actually made a mistake?
No, it just, well, I don't know. I guess it submitted it. I put it in with all the fractions and everything.
Okay.
And I've never had a problem putting it in.
Okay. I'll ask and
Okay.
see. We have a WebAssign contact person. So did anybody get that answer that we came up with earlier with the negative 4/15 to actually go through? I mean, I'm kind of trusting the arithmetic there on 1 minus 1/6 minus 4/15 minus 5/6, but we got a consensus. So, right, the ones should drop out, right?
I got the question right.
Okay. And you got negative 4/15 for the C2 value, the last constant
Yeah.
after the second anti-differentiation?
This is for number 9.
Number 9.
Oh,
Here's what we got for number 9.
yeah, it's 415.
Yeah, he has it in with multiplication, so I'm going to try it in with
Okay.
multiplication of the
We're
x's.
doing the problem right, so that's the
Yeah,
most
we're
important
doing it
thing. So we
fine.
just
You just have to put a lot of parentheses because you
Okay.
just got it.
I see what you're saying.
now I know here you're going to have to put parentheses around the x, right? For
Yeah,
cosine of x.
yeah.
Just the same way with this not being e to the x, but exp parenthesis x. So the stuff we've done all along for trig and for exponentials, just continue to do that. All right, so this process is going to be the same. Anti-differentiate again. Let's not. All right, let's go to Appendix F in the back of the book. It does have a purpose, not just to kind of fill in a day's worth of calculus. The purpose is to tie together the first couple sections of Chapter 5 so that we have a sense of what we're accomplishing with this antiderivative technique. More specifically, when we get to a definite integral, definite antiderivative, where we have a starting and stopping point, we want to be able to tie it together to something we've already done. So, Appendix F, it's on sigma notation. I did ask you to take a look at it. Hopefully it's not something completely new, but I bet you we have varying degrees in here of experience with sigma notation. So you'll have this Greek letter sigma, which is used for summations. indexed summations where you have a first term, a second term, a third term, and when we're all done expanding, we're going to add all those terms together. The index that you're using will be at the bottom of the sigma notation, so we're going to use I for that index here. It'll start with a number. The easiest one to work with is when I starts at 1, because 1 generates your first term, 2 generates the second, 3 generates the third, and so on, but it doesn't have to start with 1. So it's going to start with some integer value, and it will stop with another integer value if, in fact, it stops. We may, in some cases, want to let it run all the way to infinity. And then you'll have some way of indicating what it is we want to do with this number we're plugging in. We want to square it, 1 over x. It could be some function, some polynomial type function. So the first term would be subbing in I equals m. And the next term would be found by doing what? Those of you that have had experience with this. Keep putting in integers, 1 larger than m. And there may not be an m plus 2. Kind of depends on what we're dealing with here. What would the last term be? A sub n, right? Because when we get to here, that's an indicator that we're supposed to stop in this notation. And what would be its predecessor? One number smaller than n, right? So there may, in fact, not be this many terms, but this is the pattern of how to approach. So the definition, the only thing, I'm not going to show this because it's the same thing. M and n have to be integers, which I said, and m would have to be less than or equal to n. If that's the case, then that's how to expand it. Examples, and this, again, this is not tying into Chapter 5 yet. And we'll do more with the sum of I squared from I equals 1 to 5, from I equals 1 to n a little bit later. But this is just an example of what it would look like, what this expanded summation would look like. First term is what?
1.
1 squared. Second term?
2 squared.
And when do we stop this process?
5.
At 5 squared. So 3 squared, 4 squared, 5 squared. We get to 5, we stop it. So that's an expansion of this sum. And we could add all those together. We will have a shortcut for this, by the way, of consecutive integers squared, but we don't have that yet, so let's just add them up. There's 1, we get to here, well, that'd be 5, 14, 30,
55.
what? 55?
Yeah.
Does anybody know the shortcut?
No.
For consecutive integers squared?
A little exclamation point.
Well, that's factorial, which is going to be something else. That's actually multiplied. That'd be 5 times 4 times 3 times 2 times 1. We'll use that in here before. Actually, do we use it in 141? It's used in 241. Factorial. But we'll get a shortcut, actually, probably before we're done today, for consecutive integers squared. Might look something like this. The index of summation might be something else other than I. So 2 to the j power, let's say we started at 0. Don't see that as often, but it is possible. So what's an expansion of that look like? 2 to the
0.
0, 2 to the 1, 2 to the 2, and we keep going with this until we get to 2 to the 5. Okay? So you can't always look at the top number and say there'd be 5 terms, because that would be true only if you're starting at 1, right? Here we're starting at 0, and we have 6 things being added together. Okay, the rest of it's arithmetic from there, right? Adding together 2 to the 0 all the way to 2 to the 5th. That's not the issue. Let's start this one at 5 and go to n. So 1 over k. K starts at 5 and goes to n. The first term is what? 1 over 5. 1 over 6. Just write enough of the terms that we have the pattern. And we're going to let that run until our last term would be
1 over n.
1 over n. And we don't know what n is, so we'll just stop it with 1 over n. All right, what are some things that we can do when we have numbers involved in the argument here that, in fact, we could factor out? If you think about, probably should do an example before we leave this page. Let's say we had a 4 here, and we had, I don't know, I from I equals 1 to 3. Won't there be a 4 in each one of these terms in the expanded form?
Yes.
And if there's going to be a 4 in each one, wouldn't it be logical that we could just factor it out in front? And that seems awfully simple, but we'll be doing that with integrals later because integrals are related to these. So we've got a 4 times 1, a 4 times 2, and a 4 times 3. So certainly it would be permissible to say, let's just bring that 4 out in front and just save that. Everything has a 4. Let's factor it out in front. So that's 4 times whatever we get, 1 plus 2 plus 3. Is that all right?
Mm-hmm.
So some things we can do with sigma notation. You don't necessarily have to copy these down. They're in your book, in the appendix. If you have a c here that's multiplied times a sub I, factor it out in front. If we can factor it out in front of the sigma notation, that gives us permission to factor it out in front of the integral sign when we get there. Second thing, if we have the summation of a sum, this sounds real good. The summation of a sum is the sum of the summations. That works?
Mm-hmm.
Okay, it sounds bad, but it works. The summation of a difference is the difference of the summations. So that, again, will come in handy when we use a different looking s. When we get to the integral sign, which looks like an s, it gives us permission to do these same things because these symbols are related. So part of what we're doing in the appendix is we're going to start with this symbol, and eventually we're going to end up with this symbol. And they're both s's, and they both have to do with summations. And the bridge, or the tie-in between these two s's, is we're going to let n be infinitely large. We're going to add together an infinite amount of these things, whatever these things happen to be in any one particular problem. So if we can look at properties here, then because these things are related, we can apply the same properties when we get to this symbol, this s. Okay, here are some that we will use repeatedly. This one almost seems so simple that it's ridiculous, but let's make sure we have this one before we go on to the next couple. What would the first term be?
1.
Because there's nowhere to put the I, right? It's not in a power, it's not multiplied, it's just 1. Each term is 1. So we add 1 to itself. How many times?
N times.
N times. What is 1 added to itself? All right, let me rephrase it. Let me go back. What's 1 added to itself 5 times? That'd be 5. 1 added to itself 14 times would be 14. So what's 1 added to itself n times? That would be n. So the sum, or the summation, of 1 from I equals 1 to n is, in fact, n. You've got 1 added to itself n times.
I thought you said it's not how many times you do it, but that's the number you go to.
Well, if you start at 1 and you end at n, then you're going to have n entries.
Okay.
Because there's our first one, there's our second one, third one. When do we start or stop? We stop with the nth value. So if we start at 1 and end at n, then we've had n entries.
Okay.
So that's not always true, but it is true in this case.
If there's no place to plug in I, where do you technically start?
You start by, you use I equals 1. That's a good question. I equals 1 generates the first term. Now, how does it generate the first term here? Well, the first term, they're all the same. So I equals 1 generates that. I equals 2 generates the next term, which is 1. This doesn't help us get to the term. The term has already been defined. And I equals 3 generates the third term, and so on. So that it's almost overly simplified with that one. But we will use that when we have the sum of 1 from I equals 1 to n. We want to be able to simplify that not too far from now, and we want to be able to write in n every time we see that. All right, the next one that we'll use repeatedly is the sum of I from I equals 1 to n. So basically, it's consecutive integers. So the first term is 1, the second term is 2, the third term is 3, and so on till we get to n. Now, there is a shortcut for the sum of consecutive integers. I don't know if we can kind of develop this, but we can at least make it look believable. If we were to stop at 2, the sum of 1 plus 2 is 3. If we continue and add in the next one, 1 plus 2 plus 3 is
5 or 6.
6. There we go. 1 plus 2, and I'm supposed to be teaching calculus, right? That's what I thought to myself the other day. Somebody was on one of my bigger classes. They would put their seat, they put row 10. Well, we don't have a row 10. So my comment was, and I'm teaching calculus to this person that can't count. I didn't say it very loudly. But so there's 3, 6, there's 10. This may or may not be the best way to see a pattern. But if we add in the next number, 15, do you see any pattern with where we stopped relative to what the sum is? We stop at 2, the sum is 3. We stop at 3, it's 6. We stop at 4, and it's 10. We stop at 5, and it's 15. That may or may not be obvious. Does anybody see what that pattern is? How about if we stop at number n, like here we stop at 2, and then we take one number larger than that, and then divide by 2. That's right. Now let's validate it. Not that we're going to prove it right now. Probably the principle of mathematical induction. Has anybody done that? Mathematical induction prior to today? We may actually run through a quick mathematical induction proof and how you prove something like this. But let's see if it worked. So the last number was 2. 1 more than that is 3. Is that what we wanted? Is that the sum?
Yeah.
Let's go down here. The last number was 4. 1 more than that is 5. Does that give us the sum?
Yeah.
The last number was 5. 1 more than that is 6. Divided by 2 is... Seems like it's working, right? So the sum of n consecutive integers is that last number n times 1 more than that number divided by 2. So, famous problem. Not this problem written this way, but a famous mathematician was given this problem in the form of the expanded version, okay? Gauss. Sound like a famous mathematician? So Gauss was given this problem as an elementary student, and a few seconds later had the answer. Okay, and this was supposed to keep him busy for a few minutes. Okay, well, it didn't keep Gauss busy very long because he knew this little shortcut. So what should it be? What should the sum of the first 100 consecutive integers be? 100 times 101, all divided by 2. So what's that, 5,050? Is that right? So that's the problem of being precocious, right? Is you get this busy work problem and you find some formula and you figure out how to do it that keeps teachers, elementary school teachers, going crazy. So it does work. And you can check that, by the way. If anybody wants to check that out and add the first 100 consecutive integers together, just let me know how that goes, because I'm not going to be doing that. All right. The other one that we're going to use frequently is the sum of consecutive integers squared. So when I is 1, what's that look like? 1 squared. I is 2, it's 2 squared, 3 squared. Now this one is not one that you could at all look at this and come up with the sum. So we can validate a few of them. Let's see what 1 squared plus 2 squared plus 3 squared, what would that be? $14?
Yes.
1 squared, 2 squared, why am I having trouble with that? 3 squared, 4 squared, what would that be? 30? And let's do one more. I think we did this one earlier. All the way to 5 squared. 55. So what this is if we take this last number that we plug in, whatever it is, 5 or 7 or 11, whatever the last value we plug in for n, times one more than that, double that, and add 1. That's why it's very difficult to kind of work your way back from the sum to what a shortcut to that sum would be. There it is.
That's right. It's 5,050.
5,050, you checked it out? Okay. Good. I was worried that maybe we had it wrong.
I did too.
You did too? All right, let's check this out. Kind of an awkward formula. This would probably, if you're going to use it a lot, this would be one that, as well as the others, the others are easier to remember. This one is, you just got to memorize it. You got to learn it. Let's see if it works when we stopped at 3. What should it be? It should be 3 times 4 times 7 all over 6. Does that work? There's 12 over 6, which is 2 times 7, which is 14, right? When we stopped at 4, it should be 4 times 5 times 9 all over 6. Does that work?
Yeah.
20, 180 over 6, 30?
Mm-hmm.
It's going to work, and we can just do it one more time. 5 times 6 times what? 11? 6 is knockout. 5 times 11 is 55. So if you want to add consecutive integers, the squares of consecutive integers together, and you stop at n, there's the pattern that's going to work. So now that we've looked at those 3, and those are the 3 that we're going to use most often, here's our first one. 1 added to itself n times, ought to be n. We kind of looked at this too, that when we have a constant, we could factor that constant out in front. And when you factor that c out in front, what's it leaving here? Factor that c, doesn't it leave a 1 there? Right? When that c gets factored out front, so you have from I equals 1. Well, what is this thing right here? That's just n, right? So it's n times c or c times n. So that's really this one, is what that one amounts to. Here's our next one that we're going to use a lot, sum of consecutive integers. Whatever that last integer that you put down, add 1 to it, multiply them, divide by 2. And here's the other one that we're going to use a lot, sum of consecutive integers squared. It's whatever number we entered last, 1 more than that, double that last number and add 1, take their product and divide by 6. Now we didn't use this, we won't use that very often. That's if you had consecutive integers cubed and then you added them together. Notice how that one is very nicely related to this one. Right? I don't know. I'm pretty sure the pattern to the fourth isn't nice as this one is, going from here to here. So if you know the sum of consecutive integers, basically all you have to do is square it to get consecutive integers cubed. We won't use that one very often. So the 3 that I have checked are the ones that we'll use repeatedly. I don't really know how the time's going to work out, but let's take this. Which we know what that is. That's 1 plus 2 plus 3 all the way out to n. And let's say that we're proving, put a little question mark above there, we're proving that this is really n times n plus 1 over 2. Just because it worked in the examples that we looked at doesn't mean that it works all the time. It has to work all the time to for that to be an equal sign. So let's take this part of the equation, and this will be a proof, probably shouldn't write that word down, by the principle of mathematical induction. So we're actually going to prove that statement. The first thing you do in a proof of this type is show that it works in the first case. If it doesn't work in the first case, it's not going to work all the time. Therefore, it failed. So the first case would be where I stop at 1. So the left side would be 1. And if I stopped at 1, n would be 1. So I'd plug in 1 times 1 plus 1 all over 2. Does it work in the first case? Yes, it does. So that's true. The next thing we're going to do is assume that it's true for the first k integers. So we're kind of stopping it. We're just not saying where we're stopping it. We're stopping it at k. So, and we're going to assume that this pattern is true. Now, if that bothers you, that's fine. It used to bother me a lot that we're kind of assuming what we're trying to prove is true. Almost that way. It's not quite that way. So we're going to stop it at k, and we're going to say that it works all the way up to k. Now, we're going to prove that it's true if we throw in the next value. So here's where the proof actually comes in. So we're going to go on from this place where we stopped it at k. We're now going to go on to the next integer. Start with what we know to be true at this point. I'm going to leave some space because I'm going to add in the next value. I'm going to add in the k plus first term. Is that a true statement, what I've written so far?
Yes.
We assume that to be true in the second step. Okay, we're going to prove it true now by adding in the next term. What is the next term on the left side?
K plus 1.
Okay, it's k plus 1. I can't change this equation by adding k plus 1 to the left side without also adding k plus 1 to the right side. So I've added k plus 1 to both sides. What I'm going to work with now is the right side. These both have a k plus 1. After I factor a k plus 1 out of the first term, what's left? K over 2?
Yes.
And after I factor a k plus 1 out of the second term, it leaves a 1. So here's a k over 2. If I'm going to add this 1 to it, I better make it have the same denominator. So I'll change 1 to 2 over 2. What's k over 2 plus 2 over 2?
K over 2.
K plus 2 over 2? What do you think? Did we prove it?
Yeah.
Why did that prove it, Jonathan?
Because if you plug this k plus 1 and back into the original equation, that's what you get.
Okay. Isn't this the last number? Didn't we go all the way to k plus 1 this time? And isn't this k plus 1 plus 1? So on what we tried to prove, it was n times n plus 1 over 2. We went to the next term, so instead of having n, we now have k plus 1 occupying this position. What should occupy this position?
K plus 2.
K plus 1 plus 1. And then we should have division by 2. So it is proved true. So we prove it's true in the first case. If it's assumed true for k, and then it's proven true for k plus 1, what are k and k plus 1? I guess that's the whole crux to why this works. Aren't they any two consecutive terms? Right? K and k plus 1 are any two consecutive terms. If it works in the first case, which it does because we proved that, and if it works for any two consecutive terms, doesn't that automatically mean that it works in the second case? Right? And if it works in the second case and it works for any two consecutive terms, doesn't it work in the third case? And if it works in the third case and it works for any two consecutive terms, doesn't it work in the fourth case? So doesn't it work all the time? It does. This is a principle of mathematical induction proof. Jonathan?
Do you ever have to test it for like fractions or something like that? I mean, would it work on fractions?
You mean something that we were handed like this?
Start at like 1/4.
Oh, no. No, it's a counting. You're going to put in some kind of integer, some kind of whole number to generate that term. So that's what this notation is used for.
So
The only way we can adapt it is to let it go to n and then let n approach infinity, which we will. So we're going to try to add an infinite number of terms together eventually.
So with sigma notation, you have to use whole integers?
Yes. So you're not going to have to do a PMI proof, but that's how these things are proved, because you really can't show that they work, in the first 11 cases, the first 12 cases, because it might fail at the 21st case. So you can't actually literally write them all down. All right, last problem. I don't know that we'll finish it, but let's at least get a good start on it. This has direct implication in us putting together these S's, this capital S Greek letter sigma with this other S that we're going to have when we get to antiderivatives. We're going to have problems probably tomorrow that look something like this. That's significantly uglier than anything we've done. So, i's, remember, the i's are indexed as consecutive integers. Everything else is just a number. It's n. We don't know what n is here, but we know that it's a number and it's not affected by I going from 1 to 2 to 3 to 4. So we've got I squared over n squared. I could make 1 n over n, or excuse me, n squared over itself, so I could put those together. That's not going to help. That's actually going to make things worse. And then I'll distribute the 3 over n to these two things. And I have what? 3 Didn't we have a property that said if we had a summation of a sum, it's the sum of the summations? Okay? So the i's are the things that are changing. So let's leave the things that are being indexed where they are in the argument, and those things that aren't changing, let's bring them out front. So I can bring the 3 over n cubed and here I can bring the whole thing, 3 over n. What's that leave? That leaves a 1.
Okay.
This one's an easy one. What is that? Don't we have a shortcut for that?
N.
That's 1 added to itself n times, and we decided that's what?
N.
Which will cancel out.
Right, which works out very nicely because we've got that n over this n. And we also have a shortcut for that. Let's write that down, and then we'll continue from that point tomorrow. What is the sum of consecutive integers squared from I equals 1 to n?
N times n plus 1 times 2n plus 1 over 6.
All right, so let's pick up from that point tomorrow. But at least we're in a position where we can simplify. So I will see you tomorrow.